Welcome to the Trace Visualization app. This app replaces the time-consuming, complex, and error-prone tasks of peak alignment, peak height normalization, baseline correction, and peak labeling with a rapid, reproducible, secure, and easy-to-use tool which follows requirements contained in 21 CFR Part 11, Part 211, FDA guidance on data integrity, and numerous principles documented in the scientific literature. For example, with this tool, you can transform data like this peptide map, which with multiple detection modes has offset peaks on the x-axis, very different peak intensities, and curvy baselines, to one that has aligned peaks, flattened baselines, and normalized peak intensities. An additional feature of this tool is that labels can be added with a mouse click from a peak identity table. Oftentimes, you may want to visualize chromatograms from different instruments that may have very different dead volumes. With literally a few mouse clicks, these chromatograms can be aligned and normalized, facilitating close inspection of minor peaks that aren't always amenable to quantitative comparison by peak integration methods. Pulling data together from multiple sources and creating professional-looking graphs usually first involves a lengthy and error-prone manual exporting of data to CSV files. We've solved this problem by writing custom scripts to import raw data files and their metadata from many common chromatography and spectroscopic instruments. For Agilent ChemStation files, we further automated this task by creating a program that will create CSV files from one or more detectors for each chromatography sequence run. Let's see two examples of how to use this tool and how it compares to traditional use cases. We'll start with a peptide map with two wavelengths selected from a UV detector, followed downstream by a mass spec detector. It has signals offset by the time it takes for the fluid to flow from one detector to the other. We'll illustrate the traditional approach at high speed in the interest of time. The UV signals have the same time axes, so we can delete one of those and plot the combined data set. The mass spec base pair chromatogram has a much larger intensity, and so we'll plot that on a separate axis. Close inspection reveals the expected retention time offset in the base peak chromatogram, as well as significant baseline curvature in the 214 nanometer signal. Let's produce a cleaner, more usable figure in less time using the Trace app. We'll start by importing the same CSV file and selecting the base pair chromatogram, 280 and 214 signals. We'll peak max normalize all the signals so we can see the peaks, and then truncate the data to the desired region. A nice feature of this graph is that it's interactive, so we can zoom in to different regions. Here we can see the offset in the base peak chromatogram compared to the UV signals. Let's correct that through the peak alignment feature. We want to align the signals based on a single peak, so we'll select the peak center reference range to an isolated peak near the middle of the chromatogram. We'll drag the peak detection threshold down until the smallest peak in the range is detected. Zooming in on that same peak, you can see now that the signals are perfectly aligned. Now let's do a 10x zoom on the y-axis and see how we can correct the curvature in the baselines. We have a number of standard baseline correction algorithms. We'll go with the asymmetric one in this case since it offers the most flexibility. We'll select the 214 nanometer trace since it has the waviest baseline, and we'll adjust the lamb value as needed to get the best fit visually. With the underlying baseline artifact corrected, we now have a much easier time evaluating peak regions for a base peak MS signal, absorbance at 214 nanometers, and in some cases, absorbance at 280 nanometers, which when present usually indicates the presence of an aromatic amino acid, facilitating identification of the underlying peptide sequence. Let's move the legend to the right side of the graph, select the peak labeling tool, and import a CSV file created by a mass analyzer program that contains peptide sequences and modifications identified by mass and mass fragmentation patterns. We'll scroll down and select retention time to identify the X position of the label, and then we'll select the column that contains the text that we'd like to see displayed on the plot. In this case, the sequence range and the modification. We'll stack the plots for better visualization, and then we can zoom in to various regions to inspect the identifications. As you can see, we can drag the labels around as desired to clean up the plot. We can also use the truncation feature to inspect precise regions of the chromatogram. We can automatically reposition the peak labels to point at the 214 nanometer peaks by simply using the corresponding drop-down selector. You can add and remove text columns as desired to facilitate peak identification. You can toggle the hide reference trace, in this case to hide the base peak chromatogram, and once the plot is to your liking, you can download it as a high-resolution PNG image, which can then be opened or pasted directly into a technical report. Let's see a few more features of the app by processing 3 HPLC datasets collected over multiple days and instruments. Observe how we can select multiple files and import them, go back and add additional files if needed. We'll select the files to display them, and then truncate to the main peak region. We'll peak max normalize, align the peaks, and then finally clean up the baseline with a linear baseline correction. Let's stack the peaks for better visualization, especially when we zoom in, and fine-tune the zoom and stack amounts. And there we go. With just a little bit of work, we have a nicely formatted plot that enables good visualization of minor peak features. Trace similarity values are calculated relative to the reference trace, and these are commonly used for quantitative spectral comparisons, but can also be used for chromatographic comparisons. A record of all processing parameters are tabulated and can be downloaded for data integrity traceability requirements so that the process traces can be duplicated in the future if needed. You can also download the process data to a CSV file and import it into another graphing program. And finally, the trace comparison data is also available as a downloadable CSV file.